So today we're doing normal distribution. Woo! It was first discovered by Galileo back in the 1600s. So he was observing, I think it was stars. We've been looking at continuous random variables, right? And we've looked at a few situations like height, weight, those types of things. If you take some data, so for example, I take the data from you guys about your weight or your height or your toe size, whatever it is, and I graph that, it starts to look like this thing called a normal distribution. Or some people call it a bell curve. Has anyone heard this term? A bell curve. They call it that because it looks like a bell. So if this is your, you can see, thank you, I was like toe size from smaller to larger, you'll probably find, I don't know, something like this potentially. And it looks a little bit like this thing called a bell. Oh, that was terrible. This thing called a bell curve. So, I don't know. Does it look like a bell, the black line? So if I took 200 toe sizes, and I don't know, the most popular one was 20, but all of these rectangles add up to a frequency of 200. I would just divide all of this by 200 and it would convert it to probability, because then the frequency adds to 1. As this, the normal probability distribution has this fancy function here. Does everybody know what all those symbols mean? What does this standard deviation? You should know pi. You should know E. What's this one? This is mu. Standard deviation, and X is the continuous random variable. So, nice and fancy. So if I had this part, so it looks like this, just the first bit, what can you deduce from that? Yep, very good. So if the function looked like this, you look at the function, you can see from the function that the standard deviation is 1/2. Because the standard deviation is on the bottom and we've got 2 on the top, so it's 1/2. Does that make sense? A second. So the bell curve or the normal distribution, in the middle is the mean. In normal distribution, the mean, the median, and the mode are all the same thing. So write it down if you didn't know that. The mean, median, and mode are all the same thing. If we take all the data, and we go 1 standard deviation away from the mean, if we go 1 standard deviation away from the mean, so all of that data, it will add up to 0.68% probability of picking that data. So notation-wise, it looks like this. X is going to be between mu minus the standard deviation and mu plus the standard deviation is approximately equal to 0.68. Then we have the probability of it being 2 standard deviations away. So the probability of picking a toe size within 2 standard deviations of the mean is approximately equal to 95%. So 95% of all the toe sizes are within 2 standard deviations of the mean. The weights of the swimmers was measured and I found a mean of 85 kilograms, standard deviation of 10 kilograms. What is the probability of choosing a swimmer between 75 kilograms and 95 kilograms? Most of you figured it out. So we've got the mean plus 10 kilograms. What's that equal? The mean minus 10 kilograms. So it's asking us what is the probability within 1 standard deviation. I can be choosing a swimmer within that range, mu minus and mu and mu plus standard deviation, as we already discussed, is 68%. So if I went round and I, just picked one of these women or men at the pool, there's a 68% chance they'll be within that weight range. Does that make sense? What about B? Hopefully it's pretty obvious. We discussed is 95%. So C, which isn't there, is meant to say, what is the probability of me picking someone greater than 95 kilograms? Yep, so we know the bell curve is symmetrical. We know from A that between 75 and 95 is 68%. So anything above the 95, so this little area in here under the curve, that should be 1, because 1 is the whole area, minus what we found before, divided by 2. So if this is all 1, this is all 1, we can minus the middle bit, and we're left with the 2 bits on the outside, and then we can divide that by 2 because it's symmetrical to get just this area in here. Does that make sense? So we have 0. Divided by 2. So there's a 16% chance I'll pick someone that's greater than 95 kilograms.